Okay, good morning, everybody. This is our OCP High Performance Compute Module Interconnect work stream. And today, I've not put together a specific agenda yet. I'm just collecting the attendees here. But I guess what I'd like to do is at least if I don't particularly want to lead every single one of these work streams. I don't think it's healthy either for us. So if we can get maybe a volunteer to actually to lead this, then that would be good. I don't want to necessarily nominate anybody, but somebody from the interconnect side of the world would be good. And then I can basically get that person added as a moderator on the groups.io, so that you'll be able to see the members and communicate with everybody. Can communicate over the groups.io anyway, but also I'll get you as somebody that can control the Zoom call from a recording perspective. So on that, do I have any volunteers?
Alan,
yeah.
Last time, I think last meeting, Junhua mentioned that he is interested. But he didn't participate. Yes, attend. Yeah,
Sure.
yeah. So yeah, I'm also interested, but my issue is actually I'll be taking a long vacation after this week. So it will be like when I come back, it's already the past the first week of New Year. So but I can as a backup if you see suitable. So
Okay, that would be good.
Yeah.
So you're back when in the new year? Would you be back?
The 1 week after New Year, so it's January 7th week, I think. That's I remember. Yeah.
Okay, that I mean that could work, and I mean obviously coming up to the Christmas period anyway. It's it'll be quiet. I'm sure we won't have meetings every week going forward. But yeah, well, okay, well, thanks for that. So what I'll do is, well, I'll copy you, and I'll also copy Jinshua from Luxshare, right? And I'll just maybe give you a quick introduction to just a minutes template and give you access to the drive. I might need to get the OCP management to help me, but I'll set that up, and I can get things going for everybody, and then I can show you the ropes of where to put stuff. And that means if I can't make it, then these meetings can go ahead with you guys. Okay, so thanks for that. Sorry, is it Zineng?
Yeah, Zineng is fine, and you can call me Z. So
Z.
a lot of people call me Z, so it's easier.
Okay, there you go. I'll put that in brackets. Right, thanks.
Yeah.
Thanks, Z. Okay, so I think maybe I think most people were on the previous call except for Nat. What I'll quickly do is I'll literally just maybe I'll just share my slides just to set the context for us again, but only very quickly. I'll just flick through them so you can see the tenet, and then I'll hand it over to Z. He's done a little bit of work in the background, which is great. So we can see the update from Z, and then we can carry on the discussion from there. So let me just share my desktop in a moment. Can you see it? Can you all see that? Yeah.
Yes.
Okay. Yeah. So really what we talked about very briefly was removing all through holes from all the connectors and replacing them with surface mount. So that was one of them on the electrical connectors. The second one was specifically on the topology interconnect. We wanted to make that as generic as possible, with ideally the ability to support either PCI/CXL communication topology cables, or Ethernet being the primary two. But ultimately any standard like NVLink, XGMI, InfiniBand, etc., would also be good to be able to support. Now, from an electrical perspective, as far as I can tell, it's really just the impedance differences are a bit of a pain in the butt, and obviously the speeds. But as long as we support the highest speeds, then we should be able to support the lowest speeds. And also from a sidebands perspective, we were thinking of maybe optimizing that using the OCP approved open standard called LVDS tunneling protocol for the sidebands and maybe some clocks. So that's that. So this one's a sort of a discussion of, can we modify an existing connector or develop a new one specifically for the topology interconnect. This was just what I threw together for that topology interconnect of the basic signals I felt the minimum we would require. And then the next thing was on the EDSFF interconnect, where we've got this conductive cooling approach, so we can either plug media in or cables in, and we want it to the mechanical bodies around these interconnects today, I think are fairly varied depending on the interconnect supplier of the cables, and we just want to normalize that so it fits within the slots for these thermal conductive cooling manifold. And we'd like to attach some sort of latching mechanism in here as well, and obviously support the E3S modules as well. And then the final one was basically, we need a conductive path from this pluggable mate interface so that we can actually get that thermal transition from the E3 modules and or active cables. If we've got active cables, we want to cool them. And the idea here is, like, if you've got active optics as well as like a near packaged optic cable, you've got an active optical cable, you could, as well as an active copper cable, you could actually cool that in this much smaller mechanical format than the QSFP or the OSFP, because it will be connected to water through conduction cooling. So the idea here is we can miniaturize the optical or electrical retimers, etc., and get them into a much smaller footprint compared to the big cages we use today. And that is, yeah.
I have a question. So, as you know, there is various ways for interconnection between maybe servers or compute elements and switches in an AI cluster.
Right.
So, is that topic included in the scope of this working group?
Yeah, when you say interconnection, you mean the topology?
Exactly. Like,
yeah. Well, that
like a spinal leaf or any new stuff that has been studied in many research papers.
Yeah, obviously, if you've been following the basic interconnect we've got here, then on the right-hand side, the picture on the right, you have all of the topology interconnect, the 8 topology interconnects on the edge. And that allows you to wire any topology you want between neighboring modules, not just the fixed ones that you get in the like in a DGX or a Frontier supercomputer. So you can wire that. These modules can be switches as well, and you can be cabled or module plugs in these modules. So you can recreate any topology that exists today. Leaf, a mesh architecture, torus, 3D torus, 2D mesh. You can create any one because there is no motherboard constraining you. It's all done with cables.
very good. Anything written about this, Alan?
Well, it's no. I mean, we've got the 3D models and we've got all of the meeting minutes over the last 3 years discussing this at length. So,
Okay.
but yeah, we do need to get this into.
White paper.
We also got the presentations, but we do need to get this into specification form for sure.
Exactly. Thank you, Alan.
Okay. So just going back to that, I think that was pretty much the last slide. Yes, so some thermal interconnect where we can actually call these active devices. So that's something, and we sort of need to work with the thermal team on this. I've got a thermal substream, and I want to get some thermal simulations going here as well. I'm assuming that the active cable cooling is only going to be in the region of 5 watts, assuming silicon photonics makes its way, and the power envelope could be quite a bit less. And there are other opportunities, but maybe you could cool even more with these. But I think that the 5 watts should be fairly achievable with either the copper retimers or the redrivers or the active optics. So that covers the co-package for you, Nate, and that covers the near packaged optics variants. I don't know if are actually. I guess I believe that you're making 5 variants. You're not just doing the AIB stuff that you've done with Intel to date.
That is correct, Alan. Yes.
So your 5 variants would be interesting to, can we fit them into an active cable here? Maybe working with somebody like Amphenol or one of the other connector manufacturers to actually make an active optical cable. And we do have some co-packaged ideas that I can add another slide on. But Nat, that was possibly, I'm not sure if you've heard, but that was it's supercomputing. I was talking about the optics coming out the bottom. They typically come out the top or the side, right? So if they came out the bottom, then that could be sympathetic to the way we've designed this module with all the interconnect out of the back of the board. If we can bring the optics through the board from a co-packaged optics setup.
Okay.
But again, lots of work to be done there for sure. And it's just an idea of, can the industry do it? I guess Karen Bergman from one of the professors at one of the universities basically said there's no reason why the optics can't come out the bottom. But obviously that would be a big move for anybody. So that's the general tenet of what we're trying to get done here. I'll stop sharing now, and maybe Z, if you'd like to bring your presentation up and walk us through it, what you've done.
Yeah. Okay. Yeah. So I can share my screen. Let me just enable it. Are you okay to see my screen?
Yes, we can see it. Yeah.
Okay. So this. Okay. I should. So this is a little bit starting point. Our team did it with what Alan just presented, those requirements. So we come up some thoughts and put here, and let this group and other connected companies to chew on anything that can build from here. It will be good. So I think the main the one of the main goal is to try to remove all the through holes and become a full SMT assembly capable connect. So another thing is we pick up is from Alan's presentation is thermal that we connect interface need to provide a thermal path. to dissipate the heat. And another thing is 6-day 6-pin. Alan mentioned that it's I think it's unique for this HPC module. So we kind of combine these requirements. This slide just show you an example of 6-day 6-pin looks like with full SMT and some thermal dissipation paths. So the design is kind of scaled or based on the MCIO standard connect. And first of all, those through holes changed to the SMT. So there's a full through hole on the connect shell, and that it's converted to SMT. Like yeah, I think this maybe show better. So you will see the SMT tab extended from the metal shell here. So
okay, nice.
Yeah, yeah. So that certainly meet the requirements, and but on the mechanical strength wise, it will be reduced comparing to the through hole.
Right.
But yeah, whether this is successful, and certainly depends on the module or the whole module design, like mechanical design, how stable or how support. Beside the connect interface, the module supported by maybe other mechanism that share some force, stress force, then should be good.
Yeah, yeah. So obviously, I guess the worst forces are the tilting forces on it. So the manifold hopefully will stop any tilting forces, but you will obviously have the vertical extraction forces and insertion forces. So do you think it will be strong enough for a proper vertical extraction?
Yeah, the for insertion or mating and unmating, this we think that should be strong enough.
Okay, great. Okay, good.
Yeah.
Well, that's a good start.
Yeah,
I'm hoping that we get rid of those tilting forces because of the manifold that we will be populating.
yeah.
Okay, so if is this a 66 pin version of it? Is it? So you've actually.
Yeah, so this is a 6-day 6-pin. So you know, the MCIO standard one is 38, 74, you know, different pin numbers, but we think we can, you know, scale right from there to be a 6-day 6-pin if that the number is works best for the
Yeah, I guess there's the question of, I mean, that's the number we need. There's a question of, can we leverage an existing connector so we don't have the expense of completely redesigning the entire connector. So that's
quick question.
Yeah, go on, Mitch.
Quick question, Alan. Does this connector have power?
Yes, in the 66 pins it has power. Yes.
Okay.
That's the idea, that we can deliver sort of a nominal 5 watts, maybe. You know, it might be nice to be able to deliver a bit more, but a nominally 5 volts. 5 watts.
No, I mean for the full. I mean for the card. How does the card get power? The 40 watts for the card.
Oh, this particular one is the MCI. This is the topology connector that Z is talking about right now.
Right. So it doesn't carry power to the card.
It does carry power to the cable, but if you've got an active cable, like a paddle card with a retimer, a redriver, copper,
right,
or silicon photonics in the cable itself, this would power this. This does have.
Yeah. So my question then, Alan, is how do you get power to the cord? So kind of connector, card connector 101 from way back was that either the card floats or the card is stationary, and the connector floats. So, and then you can only have one stationary device. This is, you know, the mechanical engineers taught me this many years ago. So if you have 2 connectors and they're stationary, then you're loading them. You have a dimension requirement of the manufacturing, right? That you can't load. You
Right.
can't
So
load
the
those two
cable or
connectors.
the module floats, if I'm understanding you correctly, right?
Yeah. So I'm trying to get a picture of this. This connector is soldered down on the card.
On the module,
card is in
motherboard, correct.
Yeah,
And then the cable plugs in, or the
Okay,
this is only a cable connector in this particular this one.
Okay. So then the cable end of this connector floats.
Right.
Okay. All right.
Yeah.
And then okay. So that
This is the cable
solves that.
side.
Yeah.
Yeah.
Okay. So
Yeah,
it doesn't have to carry any load of the card then. It only carries the load of the cable.
The cable in the paddle card, which the cable's attached to.
Yeah. Okay.
Which
All right.
has the
Okay,
active components on.
Yeah, that makes sense. And then some other connector supplies power to the module.
No, the power comes from we're talking 5 watts here, Mitch. So like,
but the module is not 5 watts; it's 40 watts.
no, sorry, we're just talking about this cable one here. We'll come on to the module next. The module, in fact, the E3 module already has power pins assigned, and we're not going to change that pin out at all. So we just follow the Gen Z spec for that connector.
Okay, all right, got it.
So there's no changes except for the mechanical, the through hole pieces.
Yep. Okay, got it.
Yeah.
Yeah, go on, Z.
Yeah. So maybe if I can, so I add this here is on the MCIO, the SFF standard we contribute to. It's so far it's only the passive, but there's also a version we are working on and going to contribute to is the active one. So for active one, what our kind of solution is to provide the power is add additional pins, can kind of extend the passive connector and add a few more pins to provide power and additional pins for protocol side bands. So therefore, the passive cable still be able to use the same interface, and then if you want the active one, and then you have the a little bit longer, right, more pin that plug in. So that was I didn't show here, and I think if this is something interesting, I can also bring here to show the group what we are thinking.
That was slightly longer, I guess, in the current MCIO. Is that correct?
I'm sorry, what number?
That's slightly longer than the current MCIO.
Yes, that's correct. Yeah.
So we can accommodate the current MCIO. It depends how much longer. So a couple more things on this. I think this is good. The mechanical side is the getting rid of the through hole. I think we've addressed that, and you're saying that this approach would be mechanically strong enough for the vertical extraction as long as we can minimize the side to side, which we hopefully can with the manifold. You've also addressed the pins, so thank you for doing that. But this obviously, and this is the MCIO base, so this supports a paddle card, so we can actually build active cables because it has a paddle card. But my concern with this one is this doesn't get us up to 112 gig or anywhere, and I'm not even thinking about 224 yet, but I would like to get to 112 gig with this new topology connector. Is that going to be able to get us there for passive cables?
Yes. So mainly, this is because the PCI 6 standard, right, adopted by PCI 6 standard. So it's mainly is 85 ohm, but on our side we actually have the 95 ohm connector already delivered to the market. So that is shoot for the 64G PAM4, and currently I think we are tuning for 112G PAM4 speed.
Okay.
So it will be enabled, 112. Yeah.
I guess just looking at what's been going on in the industry. So thanks for joining, Matt and Kyle. is like the Samtecs accelerate in the Molex's near stack. They actually get rid of the paddle card altogether and put the cable straight on the pins for the higher speeds, right? 112, and the paddle card is a significant barrier to signal integrity at these very high speeds. So I guess that's my concern there is in terms of the pass bands of the various test parameters for 112 gig. You know, are we realistically going to be able to get there with a pure paddle card approach? And on the basis that both Samtec and Molex have gone away from that, the problem with their connectors is like we want a paddle card for the active piece. So I'm in this world of wanting both, but these two connector designs straddle these two different worlds. Does that make sense?
Yeah, maybe I chime in from this Kyle the perspective, right? I think if we look at modules on the IO world, they still have paddle cards up to 200 gig. It's like the paddle card definitely at 112 gig is feasible. I think where we see
so it is.
It's feasible.
It's not necessary to go to the.
Yeah. So I mean, you still see it, and it has its losses. But if we look at OCP, QDD, all those are 112 gig, and they're all a paddle card interface.
Oh, good point.
So, but that being said, right from I think more at least right now we're speaking opinion and maybe towards.
Well, yeah. The only
SP
thing on that, Kyle, is in the QSFP modules or OSFP modules, they are quite frequently active as well. I guess you do have passive versions, right?
But no, there's passive 112 gig.
And in the passive ones, they've got the bypass cables as well, where the cables go straight onto the pins again, right?
I would say the market is fully deployed SMT connectors with passive DACs at 112 gig.
Okay.
Yeah. I mean, if anyone else has counter opinion, but yeah, I think it shows possibility, right? Not that it's the best way to go or the right way to go.
Well, I guess, yeah, I guess you get improvements, which I don't know if you've got any comments on this, Matt, because you obviously do the accelerate one, which is wire straight to pin, right?
Yeah, that's true, Alan. We've seen passive straight to pin 112, 224 over pretty long distances. We have seen 112 with the cards with some of our SFFTA 1002 connectors. So I think there's approaches both ways. I chuckle at the irony of your observation earlier about wanting both for this. No offense.
Well, I always want the best signal integrity, and then I want to be
of course. But this is definitely a unique use case I think we've been looking at. So yeah.
I mean, ideally, in an improving world, it would be nice if there was an ability to have a paddle. If you had a purely passive solution, you had this ability to get rid of the paddle card, and if you and if you had an active cable, active optics, active copper, you could introduce the paddle, and obviously the beauty of an active one is you've got the drivers right next to the twin acts being soldered onto the paddle card, so you have a wonderful opportunity to get a really clean channel, although it's still a PCB launch. You've got rid of the mating signal integrity issues, which is a big one, right, with the pins. So, and I guess, so this is just, by the way, I'm sort of the agnostic one here. I'm a sort of because I come from a compute side, but it was acquired by a connector company, so I did get into the details of all of this. So I probably know more than most non-interconnect people do. But and I've done a fair bit on signal integrity. I know enough to be dangerous, at least. So I guess looking at the Accelerate one, Matt, you obviously have cracked the direct attach cable to the pin. You've also done it interestingly, whereas I think Molex's has got like a right angle approach, whereas yours is straight in, which I think is somewhat cleaner. I don't know how it compares signal integrity wise to theirs, but that looks good. But your pins are the other way around on the socket. So it looks like if we had a 2 millimeter thick paddle card, we could adopt a paddle approach. If I've got it right, or maybe I'm wrong way around. So I was just wondering, so I guess, look, we've got a number of connector experts on here. Is it worth exploring what if we are going to specify a new one? Is it worth exploring an approach where we could have direct cable attached to the pins for cleaner signal integrity on a passive cable, or paddle card attached when we want to make an active cable? Is it worth exploring or not? What's your views, guys? Don't all jump at once.
So well, what I think maybe make it a little bit more clear what the direct attach means, right? So I think if we go to the direct attach, it means this connector no longer put on the board. It's this connector will be directly attached to the cable, right? And
it goes that way around, does it?
Yeah. So, and that means if this become a direct attach, then we need to create another connector on motherboard to solder on the motherboard, right? So basically the like near stack approach, right? Is that what you mean, right? So for the direct attach.
Yeah, well, so you're right. I think you're right about the near stack. It is the other way around. But I thought the Samtec Accelerate was still the same sort of approach. Is that right, Matt, or not?
So I think if for that approach, that means you still have this connector on solder to the motherboard, right? And
that would be the ideal, yes.
Yeah. Then for the cable side, you the right now like MCIO, we put the a small PCB module there, right? And then attach to the cable. Then another approach then is you instead of create a small PCB, you create another connector, and that attach the cable to the connector. So essentially, you still have a transition between the receptacle connector to the cable. It's just you replace the another connector with a PCB, right? So so you basically need to compare the good side or bad side of the PCB versus another connector.
Right.
Yeah. So so in that approach, so I think the PCB gives some flexibilities, but I think generally speaking, the PCB may not maintain the good tolerance and gives some variations. And the connector, if you create a connector, certainly it's a better, tolerance controlled. But I think certainly PCB is more, I think cost-wise is cost effective, and connector may be a little bit more expensive. Besides that, maybe also basically they are coming from totally different process, right? So the PCB you can put a mini layer, maybe you can do some isolation layer to layer easily. But on the connector side, it's not that easy to put many layers, but you could have mechanical structures around the differential pair and side to side, between the pair to pair, and it become very good isolated. So I think it's if we compare these two methods, then it's a lot things to dig in, I guess. So.
Okay.
Alan, I also, in short, I back up what Z's saying. I struggle to think of an interconnect solution on the market that supports both direct attach cable twin ax to the contact pin, while also allowing for a migration path to an active cable. I think you're trying to find the Goldilocks connector for the application, and I don't see it. The only thing I can think of from a conceptual standpoint is if you would use a card edge connector on the motherboard, and then it's gonna be a piece. The twin ax would be attached to.
Yeah, no, well that won't make sense, right? So because you're not going to be able to unplug that card edge piece on the board.
Well, no, if you use a card edge connector, what I'm saying is, whether it's MCIO or something like an SFFTA 1002, you can terminate both a PCB and a cable, a cable. You can have the PCB has to be within the card edge connector, and the twin ax.
Oh, I see.
Or an active optical, or an active optical could be attached to the PCB in there. I think that's the only approach that's going to allow you to do both.
Yeah, and that would mean you'd have a double interconnect then for the active ones.
Well, I'm theoretically, if you use the card edge connector, like if you're putting down an SFTA 1002 connector,
right,
on the motherboard, we have cabled PCBs that fit in there, right? And we've done 112 in that type of architecture. We haven't done it actively,
okay,
but to me that would be the simplest approach.
Okay. All right. So well, Kyle, have you got any additional views, or are you in resounding agreement?
I was 3/4 following what Matt was saying. So the idea would be to put.
Well, so my perfect idea, and I'm looking at the Accelerate one now, and I can see a couple of variants of the Accelerate, and I can't really get my head around it. But it looked, when I looked at it at the one of the shows, I was under the impression that it was very similar, although it was directly attached cables that Samtec had done. It was it still had the same topology, unlike the near stack. So, but you would need something like a 2mm connector. You'd need a 2mm thick PCB to plug into it. So I was thinking, with Accelerate, if we based it off of Accelerate, for example, you could just plug the Accelerate cable in as it is today, and you've got your direct cable attached. Or you could put a paddle card in the cable, which is 2mm wide, and then solder the twin axes to that 2mm, and then you've got the paddle card variant. So you get the best signal integrity of the pluggable without a PCB. So we get better budget there. Or we can do the paddle card with the active components on the paddle card. That was a desire. But what Matt and Z were saying basically is, you would need to do a design where you have like a little riser paddle card, so you need two levels of interconnect when you attach the active. And that just sounds too expensive to me. But does that make sense, Cole?
Yeah, I think I follow, and I'm 95% sure I agree with Matt and Z.
Okay. All right. I guess I was, like you say, that Goldilocks map is a good way to put it. I'm ever the optimist. I mean, I wouldn't mind pulling the thread a little bit. I guess, Matt, if you wouldn't mind, it would be nice to pull the thread with your experts to see if what I'm saying has any viability at all. But if
I would be extremely cautious. That's my off the top of my head response, Alan.
Okay, all right. So, in which case, if we're going to go with a paddle card approach, the desire then, and I agree with you, Z, is we've got the MCIO, we've got the interconnect of the MCIO current design, which is 74 pins. We can get the impedance. The only other question I've got, guys, as well, is as we get to these higher and higher speeds, I know we've gone for this sort of nominal 92 ohms or whatever it is to actually split the difference between the 85 and 100. But does that become a compromise too far when we're really getting up these speeds up at the higher ends? Or are we getting away with it? I know the purists of the SI world want exactly the right impedance. Like you talked on IBM, they want exactly the right impedance of the entire channel, ideally. So that's this compromise approach is a bit of a struggle in my head. Now, I did hear somebody told me that the Ethernet consortium have said going forward everything is going to be 92 ohms, so they've sort of come to the middle. But I haven't heard anything from PCI. I can't imagine PCI SIG would go from 85 to 92 for us to get to one common impedance for all interconnect. Is it right that Ethernet? Do you guys know if Ethernet have definitely moved across?
I think definitely is a big word. But yeah, for 200 gig, there's, if you look at all the connector submissions, everything's in that 90 to 92 ohm. So I think that's the path it's going. I think they're figuring out how they document it and say it, and reference impedances and that whole world. But yeah, it's the direction that connectors are going, I'd say. Okay,
so do we have broad agreement that we can get at least to 112 with this MCIO, the PCI SIG SFF standard? Both passive and as well as active. Obviously active we can.
Alan, so I think maybe I can explain a little more on our approach. So we actually have two part numbers, basically two designs for two different applications, the PCIe versus the Ethernet, right? So we have the 885 ohm design, and also we have the 982 ohm design. So it's not the same connector to use for both. I hope that makes it clear.
Yeah, no, I understand that, but and that's so we can go that way. We could go that way, and modules, depending on what topology you just saw it, but they're exactly the same mechanical footprint. So you just populate what you need depending on what your chip on the board is driving. Yeah, and we're not really going to be able to drive. I was just wondering if we said we're going to standardize on 92 ohms, the routing of the module is all 92 ohm, but your driver in the silicon is 85, whether that's a better compromise than having an 85 ohm on the module and then jump into 92 at the interconnect.
Yeah, I think the issue probably will be the compliance side, right? So if you look at today's the PCI SIG requirement, they come up very tight the return loss limit line and come up as a IRL very, very tight. So I think if we deviate from 85 ohms required, the connector will now be PCI SIG compliant.
Right. Okay.
So
I think.
Yeah. No, fair enough. Well, so okay. So all right then. So we're going to say we have one connector design, but with two different impedances, and I mean, basically that's fine, because when you solder a particular chip down, it's going to be driving PCI or Ethernet. So you'd then spec the correct impedance component. So at least that gets us there. So my next question is, we don't need as many signals. We don't need the full 74 pins of MCIO, if that's the right number.
yeah.
But we do need power pins. So is it worth, I mean, from a cost perspective, it's going to be a lot of NRE cost to design a dedicated connector for ourselves. The 74-pin one looks like it works today. But if we just said, why don't we just use the 74-pin and just reserve the unused ones, and we reallocate a couple of pins to power, because obviously you don't have power in MCIO right at the moment. That was a sad oversight, by the way. We had it in Oculink, and then we got rid of it. So that was a bit sad that we that happened. Would that be a better approach, Z? That we actually just reuse the 74-pin one, and maybe we put some sort of keying on it so that it doesn't, because it's got power, 12 volts coming, it doesn't blow up things if people plug in the wrong, a normal MCIO device and gets 12 volts down the cable.
Yeah, I think connector wise, we certainly be able to carry the current, but the pin compatibility, yeah, it is an issue. I think we need to take a look at the what PCI SIG defined as a pin out, right? And that is
no. So we in that sense, we would be. So I definitely want to move. This is a topology connector, right? So this is going between HPCM modules. So it's the same interconnect, because if we go back to the spec, I said we're going to get rid of all these sidebands that PCI SIG specifies and replace it with this tunneling protocol, this LTPI that OCP has adopted. So that allows us to get rid of these pins. So we won't be PCI SIG compliant for sure, unless PCI SIG decides to adopt what we've done. But no, I'm just saying let's leverage the PCI SIG as much as possible, especially if we can get to 112 gig, because we're not going to be PCI SIG compliant and we're not going to be Ethernet compliant. There's no way we can be compliant to both at the same time. So so we get our own that covers both bases, is what I'm trying to say.
Alan, I guess that brings up in my mind, does going to a card edge style connector like SFFTA 1002, it's an industry standard interconnect. There's cabled versions that are passive that can get to 112 over a certain distance. Obviously, if you do an active, they're going to be able to go meters. Does going to something like that, using the infrastructure that's provided by what was the Gen Z connector, does that allow you to, does that give you the flexibility that you need, right? Because that way,
the problem with that, so good suggestion, and I was there way back a couple of years ago. That was exactly what I was doing. But sadly, the 8-lane connector has the extra key in it, and it makes that connector particularly big compared to your Accelerate, the MCIO, and the Molex near stack. So that was the reason why it was just too big for a topology connector. Now we could reuse the connector, and if 66-pin version of that, but then again we need to remake a different variant of the 10. So I guess we're deviating from, but we could start with the 1002 Matt and make a 66-pin version. It's this the same size as the MCIO or smaller. So that is a possibility.
And yeah, I guess I have to look at the pinouts in what you mean, because I empathize with the keying thing. But if we're able to leverage that, the connector's already made, there's cables already made.
Yeah, no, so
again,
actually, Z, if you want to pop to the next slide here. So, sorry, no,
Next.
this, I said that one. So there you go,
Yeah.
Matt, that's the TA1002 that we're obviously using for the E3 modules and the cables there.
Yeah.
But you can see there, you need 2 bays. You need two of the bays there of the free, for 8 lanes. And that makes that a huge connector compared to the MCIO. That's the problem with that, with this. But again, we could reference this version and make a single bay 66-pin variant. How many pins is a single bay actually on the TA1002? Does anybody know? It's there, I guess.
56, right? 56, if I remember.
It's 56, so it's 10 shy of our 66. So sad. Unfortunately, not done.
So yeah, so basically the TA102 and MCIO, they have very similar structure. The only thing is like different pin count and the key positions, right? So
yeah, so either we design a brand new design and we make our own 66-pin connector, or we leverage the current 74-pin MCIO and we just redefine the pins to include our power pins and our LTPI, our tunneling protocol for the sidebands. That's and I guess from a cost perspective, retooling with different number of pins would be a lot more expensive than just adding a key or something, right, Z? Or everybody?
Yeah. So that's what I'm thinking. If we really want to use 74-pin, but we want to block out any PCIe, existing module or cable to plug in, we may put some keying to kind of prevent the mismatch. So
okay, so that sounds good. All right, I realize we're at the top of the hour already. Good discussion though. So I think well maybe we can come back to this. So you're going to be gone next week, right, Z?
Yeah, sadly, yeah.
Your other slides, your one on the thermal slide, maybe just very briefly.
Yeah.
So thanks for putting this together. This is lovely what you've just done here. I think what we need to do on this though is this is a little bit more of a complicated effort. So what we really want to do here is almost design a little paddle card, or at least a little reference paddle card, because we need to have the heat sink on the active components and then bringing it to this connector that you've shown that will then mate to the water cooling frame. So obviously you've just shown this little, like an EMC type gasket. It needs to be obviously more than that. It can't just attach to the plastic. It needs to be part of the design of the PCB. With the thermal conduction from the chips to these fingers. So that's just on that. We need a bit more. So that's going to be and that needs to be designed in sympathy with the manifold as well. Okay.
Yeah, that will be inside of the plug, right?
Right. Exactly. So really, the plastic probably won't exist, or the plastic will be cut out to where the heatsink and the and the mating interface pop out.
Mhm.
So
Yes.
yeah, makes sense.
Yeah, so I think we probably need to see how the PCB get overmolded, and we see whether there's a process we can
It's a
integrate
design.
this into,
We need to design a PCB and the interconnect and the components almost in sympathy. It's like a bit of a heat sink design. It's a heat sink and interconnect rolled into one.
yeah. Yeah.
Or
I
maybe
think that
just a little copper heatsink, and then you put this mate on top of the copper heatsink, this gasket.
yeah, so I think the design wise, the concept wise, it seems feasible, but I think we really need to take a look at the assembly, how this be integrated, right?
Right.
And the thing is, I'm not sure. Like if we talk about active, if active is in this the component in this area, so maybe the heat sink will interfere with the latch. So does that mean we need to move to somewhere, or maybe
Yeah, I think we need
Yeah.
to probably maybe redesign the latch as well, or maybe they can be integrated together. But yeah. I think that's where the body of this would need. And so passive cables won't need this, right? But the active cables will. So that's what and so we need a common latching mechanism between the two, but then we need the conductive for the active, the thermal conductive. So that's good. Okay. Yeah, I'm conscious we're running over the time. So was there any other slides, or if you can maybe send me this final set of slides, Z, and then I'll attach them to the wiki for everybody to see.
Okay. Yeah, I will.
And all right. Well, thank you for putting all that together, Z. That was much appreciated, and a good discussion. So I think just in conclusion, we are going to go. We're going to try and stick with the MCIO approach, and leverage the 74-pin connector, right? And then see if we can design keying and all the rest of the pieces around that.
Okay. So I'll talk.
Yeah, if you've got any 112 gig data on your 92 ohm version, that would be really good to see as well.
Okay.
For Ethernet purposes.
Okay. I'll talk to our team and get those data. Yeah.
Okay. All right. Well, thank you for that.
Okay.
And in terms of scheduling the next call, I might just ping it back through to New Year anyway. Maybe.
Yeah. No problem. Actually, I probably will be on the email from time to time. That's no issue on email. It's just I'm out of country, so the schedule is really bad for me. So
okay, all right. Okay, well, thanks. Everyone's already dropped. So
okay.
much
Yeah.
appreciated.
Thank you, Alan.
Bye.
Okay. Goodbye.